possibilities. We heard this from the other speakers. For instance, with these just 3 qubits, there are 8 3-bit numbers, so you in general can store 8 numbers at once, and the real information are in these weightings, these amplitudes we call them. They're the weightings of the 8 numbers. 8's not very big, and if you had a parallel processor that could only do 8 numbers at a time, you can always do that much faster in a classical computer. But of course, when we grow the system to something like 300 qubits, 300 is an interesting number because 2 to the power 300, that's 10 to the 90 or something like that. This is more than the number of particles in the universe. So quantum computing has been, there's certainly a lot of hype in this field, but this statement is not hype. If we ever need to do a computation that involves 10 to the 90th or 2 to the 300 or more configurations, it will have to involve quantum computers. There's not enough space in the universe to do it classically. That's not hype. It doesn't mean we're going to have a quantum computer that does something like that, but we're going to have to use this if we want to tackle really difficult problems. So this is the good news, and I've tried to indicate in this block diagram how a black box might be able to compute 8 things at once, and you produce 8 answers. And of course, the bad news is in quantum mechanics, one of the strangest features, I think it is the strangest feature, is the process of quantum measurement. And this takes the superposition and it projects it to a singular value. And we have to do this because we don't experience superpositions in real life. And this is sort of the correspondence to the classical world. And so the bad news, of course, is if you do this massive parallel computation, you only get one answer in the end. And that answer could be exponentially small in probability. I mean, if you have all 2 to the 300 outputs, you're in trouble because you only get one answer and you don't even know which one it is. So it's random, and you might as well just do them in series on a classical computer. Of course, the final piece of good news is that before the measurement is made, we can move the quantum state around through something called quantum interference. And this happens by executing quantum gates. That's one way to do it. You basically need to change the quantum state in a very controllable way. And we heard earlier about quantum gates, quantum simulation. That's basically what they're doing. These red dots, this is very hard to depict in a drawing, but these red dots are quantum gates. They're 2-qubit quantum gates. And if these quantum gates are arranged in the right way, according to the application at hand or the algorithm, it can be possible that the output is no longer random, but the output only has one answer or a few answers, even though we have exponentially many inputs. And that's really interesting because that one answer can depend on all these inputs. So this is very vague, and there are not that many applications that can be cast in this form, but there are some. The ones we know about, we heard earlier, Shor's factoring algorithm, which of course is very important behind the security of encryption standards. The idea that factoring is an exponentially hard problem classically. You saw this slide in an earlier talk. The time required to factor an n-bit number scales exponentially with the 1/3 power of the number of bits to represent that number. Whereas in Shor's algorithm, the complexity is now quadratic, or a little worse than quadratic, but it's polynomial. And the way Shor's algorithm works, in a very simple-minded way, is to factor the number, say 39. We store all 39 initial numbers and we execute gates, and Shor showed how to put these gates together, and there are not exponentially many gates needed. That's the good news. And the gates will basically push the quantum state around based on the input of 39. The quantum gates will push the state around until we have this quantum state. And then when we make a measurement, we have one of the factors, 3 or 13 in this case. Now, this turns out the factoring problem, to factor an interesting number, of course, will require probably tens of thousands of qubits, maybe more, probably billions of operations, maybe more. So we don't have quantum computers now that can do anything that can factor an interesting number. However, there are other potential applications in quantum computing that are not as obviously proven. these will be heuristics. That is, they will work without needing a proof. And I think the one catchword for this type of application called an optimization. Now, if you optimize some very complex function over many potential variables, there are exponentially many configurations of that function, but to find the maximum or the minimum involves getting one answer in the end. So it sort of has some of the attributes that quantum computers can do, dealing with lots of configurations, having one answer at the output. Now, what we don't know is exactly how to push the quantum state around, how to put the gates together in a way that we did in Shor's algorithm. So this is very recent research on how to do this. Machine learning and AI using quantum will, in fact, go in this direction, sort of an optimization. We all know the traveling salesman problem is one of the an important, very hard logistics problem. In fact, we believe quantum computers cannot solve this problem, but maybe you don't need to find the perfect optimum or the optimum. Maybe you want an approximation of that optimum that could be better than a classical computer. In that case, it would be very useful. This morning, there was a session on computational chemistry, which turns out to be a hard problem for the exact same reason the traveling salesman problem is hard. There are exponentially many configurations of these electrons, and Emmanuel Bloch talked a little bit about simulating that using neutral atoms. It's a very complex problem already. If you can move that in Richard Feynman's sort of idea of a quantum simulator, if you can program this in terms of qubits, we might be able to solve ground states and dynamics in complex molecular systems. To me, this is also an optimization problem. And so I guess a very high level observation I'll make is that indeed, Shor's algorithm is really hard, and I don't think this will happen anytime soon. Some people think it'll be many decades. However, if we make inroads on this type of a problem for some useful case that somebody's willing to pay for, it'll create commercial value. If history is any guide, that will pay the way to get to your tens of thousands of qubits and millions, maybe billions of operations. So, in fact, getting to Shor's algorithm I think will require that we find some use in the near term that will hasten the development of much more complex quantum computers. Okay, so there's my high-level proselytizing a little bit. Quantum computing is very interesting. It will. If we need to do really hard problems, there's no other choice. I think that's kind of the thesis. Okay, so let's go in the laboratory. We've heard different versions, different types of quantum platforms that look very interesting. This table is adapted from an article published in Science many years ago. I've adapted and added a few things. It shows the many potential, probably the winning hardware candidates to build a quantum computer. And I split them into two groups, the ones on the right here and the ones on the left. The ones on the right are based in solid state systems, like silicon, miniaturizing and making more quantum, or making quantum the current silicon technology we have now. Superconducting systems, we heard a little bit about that. Superconducting systems, because they're so cold and the electrons conduct without loss, they can be isolated in a way, and you can think of building qubits that way. Now, it's interesting, in this session in quantum computing, we really heard nothing from these four on the right. It's probably fitting, to be honest, and this is my opinion, nobody knows how to scale any of these. So to be honest, I don't really see how to build a computer out of any of these platforms. You can put a few qubits together, but nobody knows how to put more than many dozen solid state qubits together and have enough gates to do anything interesting. And the problem is, solid state is not a good place to do quantum. There are quantum effects in solid state, but if you want control and replicability, reproducibility of qubits, solid states are definitely not the way to go. So I think there's wonderful research being done in all of these fields, and I think it'll stay that way for a while. But I think to scale a quantum computer based on solid state components requires a breakthrough in physics. So maybe it is relevant to this conference, the future of science. Maybe we'll see some breakthroughs here. Now, on the left, we have what has been highlighted in this meeting, actually all three of these platforms, atomic ions, neutral atoms, and photons. These are what I might call natural quantum systems. They're not synthetic like these solid state systems. These ones are not made by man. They're given to us. They're already composite quantum systems. They're already natural and perfectly reproducible. An atom is an atom, whether it's in New York or Hong Kong. It's the same atom. A photon of a given wavelength and bandwidth is the same everywhere. So, in fact, these systems, which we thought would come out of physics laboratories, these are the ones that really can scale. And there are great recipes for scaling all of these platforms. I think maybe in a biased way, I would say, I think the trapped ion system, we probably know the best how to scale it. There's serious engineering challenges, but we've moved away from physics into engineering. That's a little bit why my title is what it is. So I'm going to indeed talk a little bit further about these atomic ion traps. This type of a trap you may not have seen before. This is a pretty fancy trap made by Sandia National Labs in the US. It's a so-called surface trap. It has about 100 electrodes. It's many layers of silicon, and it's coated with gold. I'm not going to talk much about that. There's nothing quantum about this chip whatsoever. What's quantum, of course, are the atoms that are floating above that chip, in this case by about 1/10 of a millimeter, 100 microns above the chip. There's 80 of these, 80. These are ytterbium-171 ions. They occupy a space. It's been blown up and put on this figure here. This is 1 centimeter across. These ions occupy a space of about 1/2 of a millimeter sitting above that chip. And by the way, this chip is in a vacuum chamber. However, the chip can be at room temperature, and in most of our experiments, they're at room temperature. So we don't need to go cold. So scaling is actually a lot easier in this system because it's at room temperature, but you do need to have a vacuum chamber. So to build a quantum computer or have a good quantum bit, something's going to be exotic, sorry. It's either low temperature or very low vacuum. Okay, but the good news with these ions is that every one of them is exactly the same. In fact, these are very good atomic clocks. And as Rainer Blatt mentioned, there are levels within these atoms that indeed behave as great atomic clocks, and they have exactly the same spacing, no matter how many you have. So we don't have to manufacture, we don't have to worry about yield of these qubits. It's perfect in a sense. Again, to repeat a little bit what Rainer said, up here we have a circuit, time-space diagram, space up and down, 7 qubits, and we're going left to right. These are gates, and they're all done with optics. We initialize the ions to the 0 qubit state with optics, and these are gates. We're poking laser beams at given atoms depending on the program. There's a high-level software here that's controlling these laser beams. And then after the program, which is represented by these gates, after the program is done, we measure the ions. And this, again, is done by a separate laser, and the ions that glow are 1, and those that are dark are 0. And the measurement errors in these ion systems can be really low, a lot lower than we need. So what about the scaling and the engineering of the system? Well, this is a typical AMO lab. This is from many years ago, one of my labs. All of us in this session have labs that are complicated. And I think when companies, big companies that you've heard of, wanted to build a quantum computer, they did not want to do this. So I think this is probably why they went solid state. And I think they're all learning. Well, it's hard for them to save face after they've invested so much, but they're all learning that maybe that was the wrong thing to do. But the good news is, with some engineering, we don't have to have every laser beam on a totally adjustable mirror mount. And over the last few years, we have engineered that system without much exaggeration. Everything you saw on that table is in this box. Now, there are lasers on this optical table over here, but they're fed with optical fibers. And this is very similar to what Rainer showed, making the form factor small. And it's not just to make it small, it's to make it reliable and not have to adjust everything every day. And that's really what engineering is. And I will say that even the vacuum chamber is getting small. My colleague Jung-Sang Kim at Duke has miniaturized the vacuum chambers to be almost negligible. There's a little ion pump you're not seeing here, but it's also very small. And it's sealed right on the chip. And again, there's a lot of companies that have contributed to engineering this. And I'll mention in particular Sandia, I already did, L3 Harris making the optical addressing system, AOSense, Cold Quanta for helping us with this vacuum packaging. Now, with such high levels of engineering, this project was almost outsized for a university. It's very expensive to do this, and we had to get great support from agencies in the U.S. to fund this work. So Jung-Sang Kim and I formed the company IonQ several years ago to take this even further in industry. And 2 years ago, the company IonQ went public. It's a public company now. It was the first publicly traded pure quantum computing company. And looking at the economics of the money in the U.S. that's gone into ion traps, not just companies but also the government, it's pretty remarkable. Over the last many years, it's well over $1 billion have gone into this technology. That's actually what's needed to build a real system so that somebody can use it. And at IonQ, we've built many generations of systems, and you've seen pictures that look like this before. They're in their racks inside these black boxes. Our systems are on the commoditized cloud servers of AWS, Google Cloud Platform, and Microsoft Azure, so you can run small algorithms on our machines. And again, none of these systems are yet beating classical computers. So you might ask, why did you put them on the cloud? Well, number one, just making a system run 24/7 with maybe a few days of interruption every month or something like that for maintenance. That's really challenging with all these optical controllers and so forth. So that was actually a good exercise. But more importantly, and this is the applications part of the title of my lecture here, we need people that know about their problems to use our machine in our way. And that will help us build future machines around a particular problem and maybe find that application that will pay the way for future development. Now, one of the latest generations of IonQ machines called Forte, it has a capacity of about 30 or so qubits. Here's 35 ions. We use the central 31 of them, and with 31 ions, with 31 qubits, there are 465 pairs, possible pairs, and we can run a gate between all pairs. And again, these connections are non-local, so we can go directly from one to the other. Just by shining light on any two ions, we can run a gate that way. And this is the distribution of errors of those 465 gates. And so the average error rate was 99.4%, 4 times 10 to the minus 3. And you can see there's a big distribution here. What's important is that we know the fundamental error rate is a few 10 to the minus 4, 1 or 2 10 to the minus 4. So our errors are not random, they're systematic. They're still control errors. So we still have some to gain here. So that's actually, we're very excited about this. We think we can get down to that level in these systems, and then we can start to do interesting things. Now at IonQ, they've been running applications with many customers. Again, these are all small demonstrations, working with other companies and other outfits that have an optimization problem that they're very interested in. And I, again, don't have time to go into any of these. Some of them are machine learning type applications where you have a standard circuit and you optimize parameters on a classical computer. Reiner Blatt talked about the hybrid model of quantum computing. We do that a lot. So you might ask, where does this leave us at the university if the company is going to be doing all this? Well, at the university, we're doing lots of science with very similar systems, maybe not as high performance as what they have at IonQ, but IonQ is also not going to do science. They're not going to do simulations of black hole thermodynamics or things like many-body localization theories. As some of the other speakers in this session have mentioned, we and others in the ion trap community have done lots of quantum simulations, just understanding many-body physics. And I think the room for the university is to keep doing this science. We're understanding many-body quantum states, and companies aren't necessarily going to do that. They can do their own thing. So there's still going to be a lot of room for science to fill the gaps. Now, I don't have to talk much about scaling is looming. Professor Dwan already did that, but we sort of have two hierarchies of scaling. One of them is this shuttling idea, and this is actually a picture from IonQ of 4 groups of 16 ions, and we're bringing them into 32. You can see down here, 16 times 4, and this is the real picture up here. And so this is one way to have a modular scaling on one chip. This might get us to many hundreds of qubits on a single chip, but in the long run, we're going to use photonics to scale in a modular way. Professor Liu talked about the advantages of photons for communication. That's really the only way to communicate and do distributed quantum computing. And fortunately, these qubits, atomic qubits, are optically active. You can map their qubit from inside the atom to a photon that propagates. And with actually Lu-Ming Duan, we started along this line of research 15 or 20 years ago, connecting ions that were really far apart in separate traps. And this is a kind of a strategy to have a fully connected modular quantum computer in the long run. And the connection graph between all these ions it's fully connected with a flat function. No matter what two ions you want to connect to scale, there's no downtime as you increase the system. That's the advantage of having a modular system, sort of like what we do in data centers these days. So the concept here would be to have an optical switch, all classical. None of this is quantum except for the atoms inside each QPU here, and then to have these QPUs connected by optical fibers. So I think, when I was walking to lunch, all those nice quotations of tech stars throughout the world, I was struck by the one of Andy Grove. He was the CEO of Intel for many years. He said, whatever can be done will be done. And in trapped ion systems, we do know how to scale it. I don't know exactly what the devices will look like, but I won't be surprised by the physics inside there. So we know how to scale it. It will happen. I think it's just a matter of time and money. And so with my last plot here, I think we saw a version in Professor Liu's talk. I borrowed it from Hartmut Neven from Google. The number of gates you need to run, the number of qubits, they need to go up together. Red is boring. Red we can simulate classically. Purple is super exciting. It means you can do error-corrected algorithms. Shor's algorithm is way up here, by the way, so we're really far away from that. This is the trajectory of trapped ions. The dashed dots haven't happened yet, but we're sort of hitting this in-between land. We're not yet doing error correction, and I haven't talked about it much, but the errors are low enough that we think we can do something very interesting. It'll probably be in machine learning. It'll be a heuristic that you can't prove, so a lot of academics don't like that kind of applications, but so what? I think that's going to happen. It's not decades away. I think it's a few years away, and that will pay the way, I think, to get all the way up there or do other things as we want. So thank you for your attention.
Thank you so much for sharing. Please